I think this is working, yes. Okay, thank you very much for the invitation. And I am going to talk about some issues in the calculations of entanglement and Renyi entropies in chaotic systems, and in particular, some hopefully interesting subleading corrections. And I will try to tie this into some of the stuff we've been hearing about wormholes. I don't understand wormholes, and so I've been trying to come up with as pedestrian a version of it as possible for my own understanding. And so I'll tell you a little bit about that. I'm going to talk about earlier work in collaboration with my former student and now postdoc at Stanford, Chaitanya Murthy, and then some of the current work, which is still in progress with my current student, Fernando Enriquez. Being invited to this Itzikson symposium reminds me of the first time I met Claude Itzikson, of which I have a very clear memory. It was at a conference almost 40 years ago in September 1981 in Freiburg, Germany. It was a big meeting with a theme similar to this conference, bringing together people with interest in particle physics and statistical mechanics. And this was actually the first time I had ever been in Europe. I was a young postdoc. Oops, I didn't mean to do that. I was in Europe, and I was pretty nervous actually meeting all these famous people. And I very clearly remember meeting Claude and how kind and welcoming he was to me. And that calmed me down, and I had a very interesting meeting. So it's nice to remember that all these years later. Also, the work I spoke about at that meeting was done in collaboration with Eduardo Fradkin, who was also collaborating with Steve Schenker at the time on related problems. So this is really old home week for me in a sense. Okay. This is, I'm going to tell you about some work that's now a little bit older on, oh, sorry, I keep hitting my trackpad. Entanglement entropy of a subsystem, which was inspired by some work by Lev Vidmar and Marcus Riegel, and then by Peter Liu and Tarun Grover on entanglement entropy of a subsystem. So we imagine that we have some system, and we are going to think of it as cutting it into two parts, 1 and 2. One will always be the smaller system in some sense, at least in volume. And then there's an area between the two systems. The total system has a Hamiltonian H, which has a piece that refers to subsystem 1 only, another that refers to subsystem 2 only, and then an interacting piece, which we assume lives along the boundary, and we'll also assume is a sum of local terms along the boundary. And the other H's are local within the two volumes, although that's not really going to matter. And now we want to focus on a particular energy eigenstate of the full Hamiltonian that we think of, and we're going to think of this as a chaotic system, so that this state obeys the eigenstate thermalization hypothesis, which I will give an operational definition to in a minute. The subsystems have energy eigenstates, which will index with lowercase letters for the smaller one and uppercase letters for the larger one. And a minor technical point, we're going to additively normalize the interaction energy so that its expectation value in this particular state is 0. That's just a convenience at this point. Okay. And then the key input will be what Liu and Grover called the ergodic bipartition ansatz, which can be traced back to an earlier paper by Josh Deutsch. We can expand our energy eigenstate of the full system, or indeed any state, but in particular this state, in a basis of energy eigenstates of the two subsystems with some matrix M. And the key input will be to think of this M as a random matrix. Now, with a certain correlation. Now, as we've heard from various speakers, I assume Laura Boini talked this morning. I wasn't able to get up in time to hear it, but we'll listen to it later. That this is not a strictly correct assumption, and that there have to be corrections to formulas like this. But for now, we're going to ignore such corrections. This correlation function also takes a particular form. There are some Kronecker deltas that just tell us that the different ones are uncorrelated. But then there's a smeared delta function that tells us that the two subsystem energies have to add up to the total system energy. But this is not a precise delta function. It has to be smeared out. And the smearing, one of our results is that the smearing is given just by the expectation value of the square of the interaction Hamiltonian, really the variance of this interaction energy within this particular state. And this is where we're using that additive normalization to simplify the formula. Furthermore, this delta squared should scale like the area between the two subsystems. This comes from assuming H12 is local along that boundary. And if that boundary is not just a point, if the whole system is in two or more dimensions, then you can further make a central limit theorem argument that says that this is in fact a Gaussian. So we even know the precise shape of this. And then there's a prefactor that's really doing two jobs. First of all, it's sort of an overall normalization. This is e to the minus the entropy of the full system at the sum of the two subsystem energies. And at the level that we care about this delta spreading, it really should be the sum of the two subsystem energies and not the total energy, which can be slightly different. And so if one wants to do numerics on such a thing, where you care about the width of this smeared delta function, then that difference is going to matter. Okay, but mostly, I think probably exclusively, we're going to not be worried about the width of the delta function. So the setup that everyone knows is that we compute reduced density matrices from our initial pure state of the whole system by tracing over the different subsystems. We can then compute the traces of powers of these density matrices. And of course, the key result is that those two answers are actually equal. It doesn't matter which subsystem you trace over. And it's conventional to define the so-called Renyi entropies as logarithms of these things. And then the entanglement entropy is the n goes to one limit of the Renyi entropies. Okay, so the key input that we're going to use is a refinement of what was called subsystem ETH by Daimarsky, Lashkari, and Liu back in 2016. Their idea was that if you look at the reduced density matrix of, let's say, the smaller subsystem, it should take this form. The important part is this exponential of the entropy of the bigger subsystem. And so what this is just doing is counting the number of states that are in the bigger subsystem. And it's saying that the probability, if you like, of being at this particular state in the smaller system is proportional to the number of states of the larger system, because as you rearrange those states, all of those look the same from the point of view of the smaller system. And then in a suitable, sufficiently small limit, you can linearize this, and then that becomes the standard e to the minus beta h1 of the smaller subsystem. But more generally, this is the correct formula. And the wrinkle that Chaitanya and I added to this is that, what is happening? The wrinkle that Chaitanya and I added to this is that you need to do this locally in energy. If the entropy of subsystem 1, and entropy here is just log of the density of states. This is just the thermodynamic entropy defined as the log of the density of states. If that entropy at the energy that you partitioned into subsystem 1 is less than the entropy of subsystem 2 at the energy that's partitioned into subsystem 2, which is the natural case. If subsystem 1 is the smaller subsystem in volume, then you should look at the density matrix of subsystem 1. But if you pump so much energy into subsystem 1 that it actually has more states than subsystem 2, then the correct thing to do is to look at the reduced density matrix of subsystem 2, because now that is effectively at that energy the smaller subsystem. Of course, the two density matrices, if not approximated, have to have the same eigenvalues. But the larger one has extra 0 eigenvalues, and those are hard to see in an approximation like this. So you should not try to see those zeros, you should just look at the smaller subsystem, whichever one is effectively smaller according to this criterion. Okay, and then these traces, a trace over subsystem 1 just translates into an integral over the energy of subsystem 1 weighted by the density of states of subsystem 1. And so, again, in the limit that we don't care about the width of this delta function that's equating the energies, or more precisely that we're taking that width to 0, we get this formula for the trace of a power of the reduced density matrix, where these max and mins are just whichever thermodynamic entropy, whichever subsystem thermodynamic entropy is larger when subsystem 1 has energy E1. So this is in some sense the main result, or really this is the main result, that the most efficient description is to change as a function of energy, which you call the smaller subsystem. Okay, so now we could ask, how does this affect the Renyi entropies, which are just really the logarithms of these things? And let me just say in words that for n greater than 1, this results in an exponentially small correction, which I will talk about in the second part of my talk. For n less than 1, if you're interested in n less than 1 for some reason, it completely changes the answer. It's just completely different to do this switch as opposed to not doing this switch. And n equals 1, the entanglement entropy case is the Goldilocks case, where the standard answer is more or less, is basically right, but there's now a subleading correction to it, which is not exponentially small. So in the n goes to 1 limit, one gets this formula. Here, S of E is the log of the density of states of the total system. And then we evaluate this integral by Laplace's method of finding the stationary point, and that, when you work it through, just tells us that all these derivatives at an energy E1 bar, which is the stationary energy, that these derivatives, which can just be identified as the inverse temperature of the system, are all equal. So the whole system and each of the two subsystems have the same energy. But what now becomes important is the second derivatives, which are related to heat capacities, either of the whole system or either of the two subsystems. And when you work out this integral, you get the following unfriendly looking formula. So let me just point to the picture. This is now the entanglement entropy, assuming a uniform system that we've just partitioned according to volume. So, all the other features of the subsystems are the same. The general formalism applies even if you have two completely different subsystems that you stuck together. But this is the simpler case to understand. The entanglement entropy then just tracks the thermodynamic entropy of the subsystem linearly, except right very near the exact equal size. It's pushed down, and there's a gap that at the middle is the square root of the heat capacity divided by 2 pi. Now, heat capacity scales like volume, so this is a square root of volume effect There are also area effects, which we have not included in this calculation. And in higher dimension, in 2 dimensions, square root of volume is the same as area. And in 3 dimensions, square root of volume is smaller than area. But so it's most visible in 1 dimension, where area is order 1, and volume is square root or volume is the linear size of the system. And in fact, this effect is what Vidmar and Riegel saw in their numerics. And they also basically understood, not basically, they did understand the explanation that I'm giving here, that it's due to this you should partition which is the smaller subsystem locally in energy here, which is the conserved quantity. Their numerics was for a different conserved quantity, and they saw the same effect in this other conserved quantity. The reason this has generally not been seen by people doing numerics is that lots of numerics is done at the center of a spectrum of a lattice theory, where you have a spectrum that I can't draw my finger very long at the time. So it looks like this, and you're right at the top. Right at the top, the heat capacity is infinite temperature, and heat capacity at infinite temperature is always 0. So this effect goes away. You have to have non-zero temperature for this to be seen. Or if you're looking at some other quantity, non-zero chemical potential. So there's a generalization. Here's the complete generalization to having a bunch of conserved quantities called Q here. There's a heat capacity matrix when you expand the thermodynamic entropy, and what plays the role of C in that case is, I find this surprising and don't really understand why it's the case, is you just take this matrix. Here it appears as the inverse matrix, but you take the matrix and you just sum up all its elements. I'm not used to seeing sum all the elements of a matrix as a thing to do, but that's what you're supposed to do. Okay, so let me go on to discuss the newer work that I'm doing with Fernando. And this is inspired by a recent paper by Hong Liu and Shreya Vardhan, in which they invent, I think they would agree with the word invent, a replica wormhole calculus for computing these ZNs, traces of powers of the reduced density matrix, in a chaotic system, not with gravity, not with anything, no dualities, but they maybe analog of the wormhole calculus is the right word. I don't really understand that part of it, but my usual methodology is to take something I don't understand and try to create the simplest possible version of it. So they do this for what they call an equilibrated pure state, which I won't try to define. But for me, if you're in a system that obeys ETH, an energy eigenstate should surely qualify as an equilibrated pure state. So the first question, can we reproduce their results with this ergodic bipartition ansatz for the state? And they actually comment on this in their paper and basically say that you can, but we wanted to understand that better. And then the important part of this are subleading terms. The leading terms are just going to be what you get from a thermal matrix. So the question is, what are the subleading terms? And in particular, and relating a little bit back to Steve's talk, are these subleading terms self-averaging? That is, if you pick a particular state, particular energy eigenstate, and compute Zn, the leading term is definitely self-averaging. That was Liu and Grover talked about that. Liu and Vardhan also talked about it. But are the subleading terms self-averaging? And if they're not, then are they or are they not? And what does that mean? So we don't know what it means, but we tried to explore under what circumstances are the subleading terms self-averaging. with the idea is that this may be an interesting question. Okay, so again, the key input is just going to be that this matrix that describes how the original pure state of the whole system is partitioned into subsystems has a 2-point correlation function, which I wrote previously, and basically partitions the energy. And then that higher point correlation functions are given basically by Wick contractions. And again, we really should worry about under what circumstances is that a good assumption, but that will be the assumption we make. And these different Wick contractions in the modern wormhole language can be thought of, I think, as due to different wormholes. But setting that aside and just proceeding, I'm going to introduce some notation here. A quantity D sub 2 indices N1 and N2. And this will be this integral that showed up in the previous part of the talk with an entropy of S1 of E1, and then an entropy of S2, the entropy of subsystem 2 at energy E minus E1, but now weighting these entropies by different integers n's. Okay, and very roughly speaking, when we evaluate this by stationary steepest descent, whatever the right term is, we will roughly get e to the n1 s1 at the stationary energy, and similarly s2 e2, and e to the s1 at the stationary energy can roughly be thought of as the Hilbert space dimension of subsystem 1 and similarly subsystem 2. So very roughly, these capital D numbers are just powers of subsystem Hilbert space dimensions. But that's quite rough because that number, the subsystem dimensions are really infinite, and so this is some approximate effective dimension. And furthermore, it depends on the ratio of N1 to N2, even in this stationary approximation. So this is not exactly right. And then D11 is the product of the two subsystem dimensions, and more generally can be identified as e to the s, where s is the thermodynamic entropy of the whole system at energy E. And that really follows from this integral with both little n's equal to 1, just being partitioning the full set of states into the pieces. Okay, so armed with all this, one can do calculations, and here are the calculations for the simplest case of the second Renyi entropy, or these are really the exponentials of the entropy, expressed in terms of these D integrals and denominators which come from here. Okay, and so the leading contribution in the limit where we think of subsystem 2 as much bigger than subsystem 1 is whichever term has the largest second index, because that's going to raise subsystem 2's Hilbert space dimension to the higher power. So the leading term in Z2 is this one. This is the subleading term. And then we can also compute the variance. And there will again be a leading term in the variance, which again is the thing that has the highest power of D2 in it. And so the question is, this is the variance, so we want to take the square root to get the range of values. When is the range of values smaller than the subleading term in the in Z2 itself? It's always smaller than the leading term. Right. And so again, using this very crude approximation, we can write down all these things, and we get a rather strange result that we don't understand, which is that the spread in values divided by the subleading term scales like these powers of dimensions. And so this says that Z2 is going to be self-averaging if D2, which is supposed to be larger than D1, but it's not allowed to be larger than D1 cubed. And we think this is actually independent of the Renyi index, that any integer Renyi index gives the same answer, although I'm not 100% sure of that at this point. Why? Where does this ratio come from? Does it mean anything? Is it just something random and uninteresting, or does it signal something? We don't know. If anybody knows, please tell us. Another thing that had us confused for quite a while is that the paradigmatic problem here is the Page problem. Don Page, famous paper of looking at a random subsystem of a state in a finite dimensional Hilbert space with no structure, right? So all of these calculations are being done where there's a structure of energy and there's a density of states that depends on energy, and energy is conserved. And when we partition the system, we have to conserve energy, and only so much energy goes into one, and then that determines the energy. In the original Page problem, there was none of that structure. And in that problem, the answer is known and has been known for a while. Various groups have done that computation. Actually, the hardest part of this computation, maybe not, it's a hard computation in general, but the hard part is taking the n goes to 1 limit, which is what mostly they were interested in. But it turns out and this is now, for any Renyi entropy, well, sorry, the ratio is the same, I think, always. And it's 1 over D1, which is quite different than this, right? And quite a bit, and always small if D1 is big. So the Page system is non-generic in this case, and it changes the answer to put in this extra energy structure. Why is that? It turns out that this smallness of the answer, now to get this small answer does require putting in non-Gaussian corrections, and in particular, putting in the fact that the trace of row 1 is exactly 1 because it's a normalized state. So whereas if you use Gaussian matrices, the trace of row 1 will be exactly 1 average, but the trace of row 1 whole trace squared, that average will be 1 plus a small amount. The trace is allowed to fluctuate a little bit. And it turns out that those little bits of fluctuations in the Gaussian ensemble, when you remove them, it completely changes the answer for the variance. There's now a cancellation that occurs that does not occur in the Gaussian ensemble that reduces this number dramatically. That cancellation depends on the big D's here in that problem being exactly D1, D2 to the appropriate powers. And if they're not exactly D1, D2 to the appropriate powers, the cancellation does not occur. So we think that our answer here is the generic answer for any system with any kind of structure to it. And the Page answer is very special for this particular quantity. Okay, so here's a case. We all use this system as a thought experiment, as a prototype for what we think goes on in real systems, but here's a case where you have to be a little bit more careful. And is there physics in that having to be a little more careful? That we don't know. I would like to think there is, but we don't know. Okay, and since we don't know, I don't have a grand conclusion to offer you. This is work in progress. If anyone has any ideas, please contact us. And so let me just conclude as the last speaker of this conference. I will take the initiative of speaking on behalf of all of us speakers to thank our organizers for this. We know it's a lot of work to put these conferences together, and also especially those of us who were privileged to interact with Claude and all his great physics over many years. Thanks to him for his legacy of inspirational physics that has inspired so many of us. Okay, that's it.
So, thank you, Mark. Questions?
All right, I guess no one has solved our problem. I was
No.
hoping someone would say, oh yes, that's well known, it's in this paper, but
So just one question about the dip in the middle when at the beginning, where the two system sizes become comparable. Is there maybe it was obvious from what you were saying, but is there an obvious way to say this dip happens because one of the systems is lending a bit of its energy to the other one, and this is why the
yes. It's because they are it's because there's this in this formula the deviate it's because there's a deviation in the number of states, really, which is then a function of energy, and the deviation in the number of states pushes this down. So the system is a little bit more ordered here than you would have otherwise expected, is maybe a way to interpret this.
Okay. Other.
I forgot to say, I see my colleague Don Merolf and two of his students did a holographic calculation that I don't understand, in which they also saw this phenomenon. So there is also a holographic version of this.
But in that case, it would have been something that had a boundary.
Yeah, honestly, I can't tell you.
So, other questions? So we thank Mark again, and I would join Mark in thanking